Hello, software engineers. WVU1 today, so I am lecturing with this on, and I do not plan to take it off. Hi there. Hope everyone is having a good weekend. As we watch this, we're going to go ahead and just jump right into the slides. So today, we're going to be discussing modularity. So now we're going to start talking about design at a bit lower level than the overall architecture of the system. And a big part of that is talking about modularity. So what is modularity? Well, this controller is fairly modular. It plugs into a USB-C cable. This is my, my Xbox Pro Series 2 controller. I quite like it. This is my Switch Pro controller. They are different. They're made by different people, but they are both here, USB-C, which means that if I want to charge my Xbox controller, I can charge it. If I want to charge my Switch controller, I can charge it. Even more amazingly, this is my phone. There are many like it, but it is mine. Without me, my phone is nothing. Without my phone, I'm still surly and sarcastic and referring to movies that none of you have seen. Anyway, this phone also, USB-C, charges on that. The point is, they all plug and play with this USB-C. And the reason they all work with this is that they all self-contained decide how to use the input from this, the expected voltage it's going to put out, the expected current, etc. The idea is, and now that's not explicitly modularity, but because each of these are designed to fit with an interface, how they use that USB-C doesn't really matter. The point is, they can use the USB-C. They end up being plug and play. And so, with modularity, the point is, we are looking at how, to what extent, to what degree, systems components can be separated and recombined, either mixed and matched, or recombined later, with new parts that come in. So we gave something a bit of an example of hardware, all working off USB-C. Similarly, my computer, something that I want to do eventually, and by eventually I mean soon, is I would love to upgrade to an NVIDIA 3080. They are really nice looking, and they are very, very, very reasonably priced for a graphics card. And they're extremely powerful. I want one, and I want it now. But you may be thinking, wait, but what will I do? How will I make that work with my computer? Well, I can just swap it out. I can take the card I have now, which is a 1070, and I can swap it out with a 3080. That's all I would need to do. I would just swap it out because it's a replaceable part. And that's really a key component here. With Java code, an example of something that you may have done before is that you could swap out, assuming that you're just using collections functions, you're not relying on order, you're just doing things like add, removes, contains. You can swap out a list, a Java list, for a Java set, such as a hash set. And it would be faster, right? With networking, the idea is I take some existing program I have that works on one server, and I can move it to another, and it will still work. The idea is this my computer hardware, my 1070 card, is not so unique and so custom designed for my computer that it can't be replaced when I need to. And remember, we've talked about this. Your source code is going to change. You're going to need to add features. Even if it's not in this class, certainly down the line, you're going to need to add features. And so being able to easily swap something in and out is actually very beneficial to that, because that can make adding those features much more easier, and it's much less likely to propagate those changes, like we've talked about. So go ahead, take a minute, pause the video. I need a sticker like Mark has, or like Sheriff has. Pause the video, and try to think to yourself, talk to people you're watching this video with, post in the general chat, on Discord, whatever, but try to come up with other examples of modularity that I haven't talked about. So go ahead and just hit that pause button. Okay. Oops. Actually, deleted something there. Didn't mean to do that. All right. Another example of modularity, tires. There isn't one particular set of tires that work on my car. Yes, I can't put monster truck tires on my tiny little Ford Fiesta hatchback. But I can put other tires there. I can shop around looking for the best tires that fit within my budget, etc. So it's another example. Car parts are generally very, very modular. You get the idea. So the basis of modular is starting by taking a complex system, such as a microtransaction system for donations, or a study buddy finder, or a meetup finder. You can see where I'm going with that. Take some complex system and break it down into smaller, easier components. If I told you, sit down and write a micro donation system, you're probably not going to do that very quickly. But if you break that down into smaller pieces, here's the login system. Here's the browser that lets you browse where you can make your donations to. Here's the payment system. Each of those chunks is easier to take a bite out of. And you can break it down even further. And that process is called decomposition. We want to take the complicated task and decompose it into a bunch of smaller bite-sized tasks. And handle each of those individually. And we've talked about some forms of decomposition in terms of decomposing something down to, say, a three-tier architecture, a presentation, a business logic layer, a data layer. We've talked about a model view controller decomposition. And those are very broad and architectural, but we can actually go further. We can do functional and object-oriented decompositions, which are going to be the subject of the next two videos, respectively. The goal of modularity is to make source code that is readable, reliable, reusable, and maintainable. And it's made out of each of those individual components. That is, think of it as Lego blocks, and you can much more easily plug them in together. And that's because smaller problems are easier to understand, therefore easier to test and debug. And it's easier to then update because you can just swap out the old part and put in the new part. It also allows for a distribution effort in teams, such as going back to that micro-donation example. You can have one person work on the payment system, one person work on the browser system, one person work on the login or homepage, or however you want to break that up. There are disadvantages. It's not all sunshine and rainbows. One is it actually takes effort to figure out how you're going to, after you build all these tiny individual components, how are they going to fit back together? How are they going to communicate? And we're going to, by the way, talk about this a lot with design patterns, which is next week's video. Some modules, and we talk about breaking things into modules. Modules, you could typically think of it in Java like classes. Modules, if you're not careful, may end up relying on each other. And as we talked about with architecture, we want to avoid mutual dependency, certainly. Dependencies, while needed, should be limited because they make the code more complicated. I have a Chloe kitten rubbing against my leg. Here, let's see if she can say hi. It's a kitten. So anyway, it can take more time. I talk quiet because I don't want to disturb Chloe. It can take more time to design and build this system because you have to worry a lot about interfaces working together. Go on. For instance, if I just made a controller with a custom charge cable, it might be very easy for me to say, okay, this is exactly how much amperage and wattage I need for this controller to work. This is exactly how long I want the battery to last, how long I want it to charge. And I can custom design the power cable to meet my needs. If I want to design something that works with USB-C, that limits some of my design options. It can take more time and effort to do that. And so, there is a trade-off. However, I will say that trade-off almost always benefits the side of modularity whenever, especially we're talking about an agile system. So again, what can be considered a module? It's a basic chunk of code. So typically in Java, or even in Python, you would typically think of this as a class rather than a function. You can have modules that are function libraries, but generally we're going to be talking about classes, and certainly that's how we're going to talk about our object decomposition is in terms of classes. And the idea is we can take any piece of code and wrap it in whatever we need to for the language. In Java, again, that's typically a class, in order to make it a module. So what makes a good module? This is a serious question. What is good? What is good enough? What is great? What is perfect? Well, how should modules share information? I mean, if we're talking about we don't want any dependencies, then yeah, modules shouldn't share information. But they naturally are going to have to, right? The browser system is going to have to communicate with the system that connects you to the donation page. Because if you're browsing and you click on I want to donate to, the ACLU, and you end up donating to some other organization, I'm actually just drawing a hard blank right now, apologies, you would be upset about that. So it is important that we create some means to share this information. And this is a hard question to answer, and we've been working on them a long time. Some of the ideas we've come up with, much like the ideas of, we need to worry about arrow flutter when building bridges, when we were talking about the Tacoma Narrows Bridge, for example, were learned by doing the wrong thing, finding it not worked, and then coming up with an idea that does. So, ideas for what is a good module? It encapsulates just one system, task, or function. It does one thing. It explicitly focuses on a very narrow, specific thing. It is reusable, that is, it can be used in multiple parts of the system without negative repercussions. It is easily testable, and it hides design decisions from the rest of the system. We're going to talk about that as information hiding. And that is to say that it can be modified without affecting the rest of the system. We talked about this with layered architecture. The idea that if the interface doesn't change, even if the function changes, even if the implementation changes, if the interface stays the same, then we can plug and play and not worry about any differences. So how do we measure the quality of a module? How do we measure how modular it is? Well, we look at principles of information hiding, cohesion, and coupling. And we're going to work through these one at a time. Information hiding. Remember when you took 2110, we talked about that private keyword, right? The idea that we actually don't make variables or even some functions visible outside of the class. Those are examples of information hiding. Cohesion, that is to say that the module is cohesive. It focuses on one thing. I am ADD. I am very not cohesive. I got distracted by my cat just a second ago, right? I was trying to do two things at once. Not cohesive at all. I ruined this lecture, didn't I? Coupling is how complex is the interaction between two modules. And when we're talking about cohesion, high cohesion, very, very tight focus on one thing is good. And when we're talking about coupling, low coupling or loose coupling is actually good. That is to say that the interactions are very simple, not complicated at all. So with information hiding, we want to separate how something is implemented from how it's used effectively. It's the idea that we are going to separate the design decisions that are likely to change, such as what data structure you use, what source of information is the data coming from. Is it a text file? Is it a database? Is it a server? The user interface. Things like that. Things that are likely to change. We want to protect the system from when those changing, causing a propagation effect. And so we do that through information hiding. And that's what we talked about with the stable interface. The interface is not likely to change, even if the underlying implementation does change. And it is part of the foundation of both structured design and object-oriented design. We've talked, most of what you've done since 2110 is object-oriented focus. When we get to design patterns, it is going to be OOAF, object-oriented April Fools. That will say that's what AF stands for. But the point is, in structured design, when we're talking about individual functions, we design those functions from a standpoint of black boxes. Here's the inputs, here's the outputs. As much as we can, we want to avoid side effects. And, if we have side effects, that's going to violate information hiding. In object-oriented design, we are going to have side effects, but the idea is we encapsulate those within the class, and we make each class as modular as it can be, and we usually will often hide classes behind a layer of abstraction, such as rather than using an array list, you just use a list, or even better, you just use a collection. Something returns a collection of something that has add, find, contains, an iterator, but otherwise, you don't know if that's a list, a set, whatever. So that way, if it changes, we're fine. And again, the similar idea here, we've given this example before, is if you haven't driven a Tesla, but you've driven an automatic transmission car, you can drive a Tesla, because the interface is the same, even if what happens when you press the gas pedal underneath the hood is very different. Understand that information hiding doesn't depend on using either structured or object-oriented design. It's just, it doesn't depend on any particular design methodology. So when we're talking about design patterns later, next week, that's going to be very object-oriented, but that doesn't mean that we're therefore ignoring the structured design elements of designing our functions like black boxes. So again, the idea is, let's say we have some piece of data, and we have a bunch of functions that access that data, and the rest of the program accesses the data through these functions. First, this is already a pretty good design. This almost looks like our three-tiered architecture, right? You could think of this as the rest of the program. Maybe that's a user interface or whatever. This would be our business logic that helps us access the data being hidden from the rest of the program behind these functions. So already, this is pretty good. But from there, we could think of our data as, okay, we need to insert some element I, we need to delete some element J, we need to find the location or determine whether or not the data contains some element K. These are the access functions. Whether this is an array, or a file, or a list, or a structure, or a server, or a SQL database, or any of those things, we simply use these functions. And the advantage of this is if instead of using an array, I decide later to use a file, or I decide to use a list, or I change it out for any number of other things, so long as I maintain this interface, these access functions, and I don't change them, and these are likely very stable, right? We do need insert and delete and find. Those aren't going to change the interfaces, even if how they work changes. This is a very good modular system. Again, ignoring what the remainder of the program is, because each of these functions serves one very clear specific purpose. Each of these functions works with a single, easy to understand interface where all the information is passed through the arguments and the return values. They are black boxes. Yes, insert has side effects, but those side effects don't affect the rest of this program. How this file changes or how this array list changes or whatever doesn't affect the remainder of the program. So that's a good idea in terms of how we would do our design. This helps towards modularity. From there, we have coupling and cohesion. I've already mentioned this. We want loosely coupled, little coupling. That is, two modules are generally having only very simple interactions, and we want cohesion where we group things into a single module. You know, if that module has multiple functions, those functions are grouped together because they have a very good reason to be grouped together, because they all deal with the same thing. And there's different levels of coupling. The lowest example, data coupling, that's what we talked about earlier. The idea is two modules only interact with each other by means of passing data as parameters or as passing information back as a return type. That is data coupling. That's the gold standard. That's the best. As we get further down this list, there's more complicated interactions between two modules, and it gets harder to maintain. There's stamp coupling. This one is a bit weird because I'm going to talk about common coupling later, and you're going to think that the two are related, but they're not. So yes, its two modules share a common data structure or some element, but the key is they are working on different parts of that shared data structure. This isn't particularly common, but it is something to at least know what stamp coupling means. Control coupling is when if one module decides the function of some other module, such as data passed affects some control flow statement, or maybe passing a boolean or a flag. This is a little bit less desirable than data coupling, but still broadly it can be okay. It does increase the complexity though, because if from the external you say, okay, I need to pass this boolean function or this boolean value true in order to do this functionality and false to do this functionality. If you have to know that, you're now dealing with a more complicated relationship than just, hey, module over there, here's my data. Okay, thanks. You know, and it passes you back something. I thought about trying to do some magic trick and just like mounting a couple over here and changing it out, but I didn't have time. Anyway, common coupling is when, yes, like stamp coupling, you're sharing a single data structure, or maybe it's some shared global data, and you're directly modifying it. And this is specifically global. So this data exists, both the modules have access to this global data, but it's not possessed by either module. That's bad. That's called common coupling. Even worse is content coupling, when, you know, this module has a pair of scissors. I need to get better props, I know. And this module over here says, oh, well, we need to open that pair of scissors. And it comes over and it opens the other module's scissors. It's directly manipulating the variables in this module. That's really bad. And if you do anything like that, you should generally avoid it. Rather, you can do things like control coupling, which is preferable, and let this module say, okay, hey, here, call this function with true. True for open scissors. And then this module opens them. That's better. Not to say perfect, but it's certainly better. With cohesion, and this one, there's two slides. So everything on this slide is generally fine, although with cohesion, functional cohesion's always the best. The idea is it's the highest degree of cohesion, and it's what you should strive for, and elements of a module in a functional cohesion are grouped together because they contribute to a single well-defined function. For example, if I were to have a program that reads in a bunch of tweet information, and I use that tweet information to determine what the most common trending thing is. What I just described is not a module. That's the whole program. The part of the program that generates the tweet information from either a file or from the public Twitter API or whatever, that part of the program that generates the tweet information, that's a single module. And all the functions there relate to reading in the information and generating lists of tweets. This module doesn't use the tweets for anything. It just generates it and then passes that to the module that actually does any information processing. That's good. Sequential processing, and by the way, this is going to sound similar to procedural on the next page. We'll talk about the difference when we get there. But sequential is when a module groups functions together because, you know, if my hand is a module, my thumb uses the function that my thumb function uses the index finger function. The index finger function uses the middle finger function. The middle finger function uses ring. The ring uses the pinky. And so I put all these in the same module because someone outside is going to say, oh, I need to pass some information to thumb. It passes information to index, then middle, then ring, then pinky. Pinky's done. It passes back, passes back, passes back, passes back. We put all these together because they are sequentially grouped. They all call each other. You could argue that maybe some of these individual functions are, you know, with the thumb being the most broad, and maybe pinky is so specific, it should be in a separate module. Maybe that's possible. Communicational cohesion. This is when we are grouping different functions together into a module. Again, I'm thinking of this from a Java perspective, but it doesn't need to be that specific. But if we're talking Java or even Python, you're grouping functions together in a class because that class all deals with a common data source, a common I/O source, a file, a server, database, whatever. Procedural is when we group together different modules to ensure order of use. Now, I want to be clear the difference between this and sequential. Sequential is specifically this thumb calls index, calls middle, calls ring, calls pinky. It's actually a call sequence. Instead, if I were to say write a bunch of commands, twitch the thumb, twitch the index finger, twitch the middle finger, and so on, those are all independent. They're not calling each other. But because I want them to occur in a specific order, that is, I want to go from this side of my hand to this side, then even though they're all kind of their own thing, twitching an index finger, twitching middle, whatever, I'm doing them all in a specific order. So I group them together to ensure that that order is executed in the order I want. Similar is temporal cohesion. You group together things that occur at roughly the same time. Somewhat similar, but a bit more specific. Then there's logical cohesion. We group by function, but different functions may not be related. So while logically categorized things go together, there's several independent things. Let's say, for example, if I were a robot, I might. Well, that's actually a bad example. I have one module, or I have one function that takes this Coke and pours it into this glass, and I have another module that drinks the Coke. Refreshing. Coca-Cola. Give me money. No. But really, the act of pouring it into this cup is very different from the act of drinking it. Even though the two occur likely together, they're just grouped together if I put these two functions same because they both relate to drinking the Coke, but not really. They're not necessarily linked at a low level. They're implemented very separately. Their implementations maybe depend on each other a little, but they can be implemented independently. So we probably should have two different modules there. And then finally, coincidental cohesion. This is the big ball of mud. By the way, if you're having trouble visualizing a big ball of mud, go watch videos of Katamari Damacy, and that's what the big ball of mud is. Katamari Damacy. It is a popular game from the mid 2000s. Anyway, we're just grouping things together by chance. So it's unplanned. The cohesion is random. This is the worst case. So again, best functional cohesion. It gets worse as we go down the slides. Coincidental being the worst. All right. So now I want you to pause the video, and we're going to ask yourself, what makes up a module in Model View Controller? You're working on your project. Your project is in Django. Django is MVC based. What makes up a module in MVC? Does MVC have high or low cohesion? And how would you know? And does MVC have high or low coupling? How would you know? Talk to your classmates about this. Again, get on Discord, watch this video with someone else. Social distance, of course, wearing masks, etc. Or on Discord, whatever. And pause the video and figure that out. Okay, all right. So now the video is unpaused. So what are we going to do? How do we actually break things into modules? Where are some practical examples? Well, we're going to do that next time. And we're going to start by first decomposing into different functions. We're going to take a task, break it down into functions. And that's going to be the functional decomposition. And then after that, we're going to look at a process and decide how to break it down into classes or models that emulate how we want to model the problem. So that's going to be next time is, well, functional, and then after that, object-oriented. I want to be clear that if two people are given the same task and they decompose the problem differently, there's nothing wrong with that. It is possible that both people produce systems that are modular, that have high cohesion, low coupling, that look different. And that's fine. Given any problem, there is no one perfect design. But there are bad designs. So you do want to make sure that you're picking a solution that is, efficient in terms of how you're breaking things down, its ease of modification or maintenance, how it fits within the constraints. Things like especially if you're dealing with embedded systems, the limited computing power, etc., available languages and technologies, etc. So we'll see you next time. Thank you all for watching, and take care. Hope you are having a great weekend.